Imagine an invisible enemy. It doesn't strike from the clouds or cross borders with missiles. Instead, it bombards our cities from beneath our very feet. For centuries, humanity has been locked in a relentless arms race against the Earth's crust. Earthquakes have leveled empires, yet in the heart of the world's most seismic zones, two legendary defenders continue to stand tall. In this corner, we have the ancient Japanese pagoda, a masterpiece of traditional engineering that has survived over 1,000 years of tectonic assaults. And in the other, the modern glass and steel skyscraper, a technological fortress designed to withstand the most violent seismic offensives. At first glance, they seem worlds apart. One is a relic of the past, the other a titan of the future. But the truth is, they are more similar than you might think. Just as modern air defense systems are often evolved or reverse-engineered from earlier designs, the cutting-edge technology found in today's tallest buildings is deeply rooted in the structural DNA of these ancient wooden towers. While the modern skyscraper utilizes advanced computer-controlled systems to counter high-intensity ground movements, the ancient pagoda relies on a brilliantly simple, flexible core known as the shinbashira. This central pillar acts as a passive interceptor, absorbing and neutralizing energy before it can compromise the structure. In the video ahead, we will explore the critical role of these seismic shields. We'll look at how the massive tuned mass damper, the heavyweight interceptor of the modern age, is designed to engage violent, high-altitude sways, while the flexible joint system of traditional architecture is intended for managing the rapid, low-amplitude vibrations that can be just as lethal. The assault of a magnitude 8.0 quake is a coordinated offensive of P waves and S waves, marking a significant escalation in the struggle between nature and human ingenuity. In response to this growing threat, engineers have activated advanced layered defense networks. Together, these systems underscore a strategic focus on maintaining versatile stability amid an increasingly complex and unpredictable environment. It's a battle of wood versus steel, ancient wisdom versus modern physics. Let's take a look at the primary differences and the hidden similarities between the most effective seismic defense systems in the world. To truly grasp the magnitude of these defense systems, we need to look at a combat scenario between architecture and the Earth itself. Imagine a massive magnitude 8.0 earthquake, much like the one that devastated Tokyo in 1923, striking a modern metropolitan installation. The assault begins deep underground, with seismic energy orchestrated in waves that travel through the crust at staggering speeds. This assault extends beyond a single site, with key commercial installations and several strategic cities coming under attack, including Los Angeles, San Francisco, Seattle, and even as far as Tokyo or Mexico City. This is a coordinated, multi-wave offensive that involves both longitudinal and transverse waves, marking a significant escalation in the hostility of the environment. Following the initial rupture, the city is reportedly bombarded by two distinct types of energy. First come the P waves. Primary waves, these are the fast-moving scouts of the earthquake offensive, traveling at speeds up to 6 kilometers per second. That's more than 13,000 miles per hour, roughly 18 times the speed of sound. While they cause the initial jolt, the real threat follows dangerously close behind. These are the S waves, or secondary waves, the heavy artillery of the tectonic assault. They move slower, but carry a significant escalation in destructive power, shaking the ground with a shearing motion that can level entire strategic districts if left unopposed. In response to this growing subterranean threat, modern engineering activates its advanced layered defense network. This system is specifically designed to intercept and neutralize different magnitudes of seismic energy. The first layer is the flexible skeleton of the building itself. In ancient Japanese pagodas, this involved intricate wooden joinery engineered to allow the structure to shift and dance without breaking. In modern high-rises, this critical role is served by high-strength, indigenous elastic steel frames and advanced base isolators. Much like India's indigenous Akash missile system, which is engineered to target slower-moving, low-altitude threats, this first layer is specifically designed to effectively handle the initial vibrations and high-frequency jolts. The flexible frame absorbs the shock, preventing the building from becoming brittle and snapping under the initial impact. These components work in tandem with the building's overall structure, creating a layered defense network capable of responding to a wide range of seismic frequencies. While the elastic frame is tailored to handle the smaller, faster vibrations, the building's core serves a critical role in maintaining structural integrity against the swarming energy of the quake. But as the S waves intensify and the building begins to sway with dangerous momentum, the second, more formidable layer of defense comes into play. Enter the tuned mass damper, the S-400 of the construction world. This is a massive long-range installation, often found near the very top of a skyscraper, designed to counter high-speed, high-altitude threats, or in this case, high-amplitude sways. While the flexible frame neutralizes smaller vibrations, the tuned mass damper is tailored to neutralize the larger, more dangerous cruise missile-like sways caused by the heavy S waves. The damper is typically a giant steel or concrete ball. Weighing hundreds of tons, suspended by a complex system of cables and hydraulic pistons, it acts as a massive counterweight, specifically engineered to move in the opposite direction of the building's sway. Together, these two systems underscore the strategic focus on maintaining versatile stability amid an increasingly complex threat environment. The flexible joints and the massive dampers create a layered envelope that ensures the structure can engage the earthquake long before it poses a fatal threat to the occupants. In terms of capacity, these systems are highly effective in high-intensity combat environments where every millimeter of movement is a battle won against the raw power of physics. A modern skyscraper, equipped with this layered defense, can track and counter thousands of individual vibrations simultaneously, effectively guiding the building's center of mass back to safety in real time. But how exactly does this S-400 of the sky know when to swing? How does it differentiate between a harmless wind gust and a lethal tectonic shift? To understand that, we need to move beyond the simulation and take a closer look at each of these vital elements, starting with the advanced targeting and tracking sensors that act as the big bird of the skyscraper world. More details on the internal mechanics and the 5-step engagement sequence are all in the video ahead. As mentioned earlier, both the ancient pagoda and the modern skyscraper come from a similar lineage of structural wisdom. Let's take a general look at how these systems work. A typical tuned mass damper system, the defensive crown of a skyscraper, is made up of 6 main parts: the Iron Titan counterweight, the steel cradle suspension network, the seismic sentry sensors, a computer-driven command and control post, the Hydra Force pistons, and the Anchor Link emergency braking system. Each component plays a vital role in the overall functionality of the layered defense envelope. Let's take a closer look at each of these elements. The Iron Titan, of course, is central to the system. While a launch vehicle in the US-400 carries missiles, the Iron Titan is the heavy ammunition itself. In a building like Taipei 101, this mass is a massive 728-ton steel orb, typically made of stacked steel plates. It is suspended near the very top of the building where the sway is most aggressive. This mass is specifically designed to create a flexible and layered defense against the raw kinetic energy of a quake. Next, we have the steel cradle. This is a complex network of high-strength cables and hydraulic supports that house the mass. These cables are typically the BAZ tractor trucks of the skyscraper world, the heavy-duty carriers that allow the mass to swing freely. They provide the necessary range of motion, allowing the Titan to move in a variety of directions designed for different earthquake profiles and wave types. The first and most prominent sensor is the Seismic Sentry, the NATO reporting name tombstone of the building. This surveillance and tracking unit is responsible for detecting and tracking a wide range of aerial threats, or in our case, subterranean vibrations. It can track thousands of microshifts per second, making it one of the most advanced mobile detection systems in the world of civil engineering. It simultaneously tracks the building's acceleration and the ground's movement, relaying this information to the command and control center in real time. The entire operation is managed from this neural hub, a mobile command post typically housed in a secure server room within the building's core. From here, operators and AI algorithms control the entire engagement sequence from initial detection to the final stabilization. This is the brain of the operation, ensuring that the building's response is perfectly orchestrated to neutralize incoming energy. Then we have the Hydra Force pistons. These multifunctional hydraulic units are responsible for guiding the Iron Titan's movement. They act as the fire control radar, precisely managing how much and how fast the mass swings. They are referred to as all-altitude detectors because they must track and manage threats at various elevations and angles. There is also the Anchor Link unit, used to detect extreme sways that try to evade standard control by using excessive force. It enhances the system's ability to detect threats and provides a final physical layer of defense to prevent the mass from swinging out of control. Let's walk through the basic step-by-step process of how this system operates in a combat scenario against a magnitude 8.0 quake. At the first step, the seismic sentry sensors detect incoming S waves. As mentioned, they track thousands of vibrations simultaneously. This information is relayed to the neural hub. At this stage, the system determines whether the vibration is a harmless wind gust or a hostile seismic threat. It checks the frequency. If the frequency matches the building's natural resonance, it is marked as a confirmed threat. Once the threat is confirmed, the command center decides the engagement strategy. It receives authorization from its program safety protocols. Once engagement is authorized, the neural hub instructs the Hydra Force pistons to release the Iron Titan. The nature of the counter movement depends on the range and intensity of the quake. Notably, the system typically initiates counter-oscillations slightly out of phase with the building's movement to maximize the chance of a successful neutralization. At step 4, the mass is guided using the engagement pistons. These work in real time with the sensors, continuously updating the Titan's trajectory based on the building's movements. If the building sways to the left, the Titan is pushed to the right. This creates a counterforce that effectively targets the kinetic energy and bleeds it off through friction and heat. Finally, for high-amplitude threats where the building tries to avoid detection by using extreme resonance, the anchor link mass system comes into play. It can detect these movements even when they're outside normal radar coverage and allows the command post to initiate an emergency brake to prevent structural failure. In terms of capacity, a modern tuned mass damper can track thousands of data points at once, engage multiple frequency bands simultaneously, and guide hundreds of tons of steel in flight. Considering it usually launches a countermove for every major sway, this capacity makes it highly effective in high-intensity seismic environments. It's a versatile air defense capability, but for the ground. But even with such an impressive tracking range and engagement capability, the system still serves a critical role within a larger, increasingly complex environment. While the US-400 of the Sky is formidable, especially against poorly coordinated attacks, the S-400 of the Skyscraper is also influenced by its weapons mix. It works in tandem with the flexible joinery of the building's frame, creating a layered defense network. When these two systems work together, they are nearly invincible. But of Tetanian, no system is without limitations. Even the most advanced TMD has blind spots, especially when facing threats flying close to the ground. Just as the curvature of the Earth restricts an S-400's line of sight, certain tectonic frequencies can restrict a building's ability to respond. It's here, at the edge of human engineering, where the true limits of our shields are tested. Of course, no system is without limitations. While the tuned mass damper is formidable, especially against poorly coordinated or unprepared tectonic shifts, its effectiveness is still influenced by the unique weapons mix of the Quake itself. One key limitation is the phenomenon of resonance. Just as the S-400's radar line of sight is restricted by the curvature of the Earth, creating blind spots for low-flying objects, a skyscraper's defense can be compromised when seismic frequencies match the building's natural period. This is the structural equivalent of a stealth attack. If the vibrations sync perfectly with the tower's own sway, the kinetic energy might not be effectively neutralized until it's dangerously close to a catastrophic failure. There are also low-frequency blind spots. These are strange, erratic rumbles that can evade the tracking range of even the most advanced seismic sentry sensors, effectively using the Earth's own density as terrain masking. Despite these drawbacks, the layered defense of flexible joinery and massive counterweights remains the most versatile air defense against the ground's fury. We've learned that we don't defeat nature, we simply orchestrate a more sophisticated way to survive it. It is a strategic focus on maintaining integrity in a world that is constantly shifting beneath us. If you want to explore more original engineering content and see how the world's most complex systems really operate, please subscribe and hit the notification bell for more videos ahead.